Hello, sorry, it's the usual technical challenges that make life a little bit more interesting than just a lazy and nice, well-going everything's. Okay, I would like to talk a little bit about experiences recently discovered in very special climatic regions such as Southeast Asia and also Middle East regions. My world still looks like that. Yeah, I'm one of the dinosaurs working with analog holdings, and I know that I will extinct soon, but I'm not sure who will extinct earlier, those media or myself. This is what I would not like call a ideal storage situation. Neither this. Both situations I found in some archives in Southeast Asia while walking on a living carpet. The carpet was living because there were insects inside. So in this, exactly this room, what you can see here is termites eating the paper and eating everything around, and their digestion results end up on the media. So what have you been doing in Southeast Asia? I have been cleaning termite shit. So, but what are our most important problems in storing and keeping our media physically alive? So one of them is the well-known vinegar syndrome, which occurs with the base material and cellulose acetate. All video archivists can be happy because fortunately there is no video on cellulose acetate, but certainly enough of our film holdings. The vinegar syndrome is a quite complex complex situation of interaction, and I don't explain it too much due to the copy process. This has changed now. Don't ask me why. Usually the presentation was well, so now we cannot read the lower part. Just ignore it. You can read hundreds of literature about the vinegar syndrome and the chain scission, and it's usually a two-tier or the reaction is at least divided in two parts. One is the chain scission of the material, which is autocatalytic, which is driven by the acetic acid that is evaporated by the material. And the other one, this can be the result, then the final result, but the other reaction, the more the chains break, the more volatile substances, like for example plasticizers, can evaporate. And this makes the material even more brittle. You have the breaking of the chains, and additionally, this opens the way for evaporation of plasticizers. This is a reaction which is very well understood in the 1960s. So 1967, there is a basic literature which I would recommend to everybody from Mr. Voigt and Mr. Höchst, Physikalisch-chemische Ursachen der Alterung von weichgemachten Kunststoffen. In this publication, they explain in detail how the evaporation goes on. Nevertheless, it is mostly underrated with cultural heritage materials. But the results, all of us, we know them, are looking like this, or like this, or eventually like this. It's getting worse and worse, and sometimes also like this, yeah. So, what is the diffusion of a plasticizer depending on? It's depending on the size of the surface exposed to the atmosphere. The more exposure to the atmosphere, the more ventilation you have, the more volatile substances can evaporate. So there is the question, ventilated can, yes or no? For me, it's a big discussion and a big issue. Yeah? Certainly, we want to have ventilated cans, but we have to know that with a ventilated can, plasticizer and acetic acid, as bad as it is a plasticizer, as well as humidity. Anyway, the thickness of the diffusion zone, for example, The diffusion coefficient rises with the plasticizer concentration, so it depends a little bit on the production of the material, the saturation concentration and vapor pressure of the plasticizer inside the molecular system, the plasticizer concentration and vapor pressure of the atmosphere outside, which means high temperature, high humidity, high vapor pressure, high evaporation. Temperature and atmospheric pressure, which means that vacuum accelerates this process. So vacuumating your items is not the best thing. Or you have to decide what you want. You have to die one death. The question is, which one? The bigger, the higher this factor, the faster they proceed. So a very tiny look on the production and on the use of external plasticizers. Cellulose acetate has been externally plasticized, which means that this is a mixture. The plasticizer interacts physically, not chemically, reacted with the polymer. It's basically a polymer mixture, and you see this tiny molecules, the round parts here, they help the chains or the comparatively harsh material to get a little bit more flexible. And this is the reason why it can evaporate, because it's not chemically reacted. It's only the bonding, the molecular bonding inside the material that holds it or not. So evaporation depends on various parameters. I have already outlined some of them, but the red ones are very interesting. The lower the molecular weight, the smaller the plasticizer molecules are, the cheaper and easier they are in production, but they are very highly volatile, which means that early plasticizers or smaller plasticizer molecules have the tendency to earlier evaporate than later produced tapes. Here you see it. If the molecule is a little bit bigger, so you have a longer chain, then it does not evaporate so easily. There is lots of literature you can find about these processes. So how does, for example, a magnetic tape shrink? Let's have a look at the composition. We have the substrate, which contains solvents, cellulose acetate, and plasticizers, like, for example, 3-phenyl phosphate, with up to 20% of weight. 15 to 20% of the substrate is plasticizer, while the magnetic coating usually consists of magnetic particles, of metal, of corroded iron particles. They don't shrink. You have a much lower percentage of lubricants and plasticizers, only about 3%. So what happens if the plasticizers evaporate from the substrate? The result is brittleness, deformation, shrinking, loss of elasticity, loss of tensile strength, and in the worst case the tape becomes unplayable, and the shrinkage is always towards the layer which has where the most part of plasticizer can evaporate. So the magnetic coating shrinks to a lower degree and stays inherently stable, and this is the reason why it keeps the wider way while the substrate is shrinking and the material is deforming. This looks, in the end, it looks like that. This is a magnetic tape, which is very brittle. You see it is already broken on one part. The upper side is the substrate, and on the lower side, the longer way, is the magnetic layer. Here are some more examples of shrinkage, and here the next one. And here, a wonderful example for diffusion of plasticizer depending on the size of the surface exposed to the atmosphere. Here we say that the inner part maybe never has been played and never has been exposed to the atmosphere because it was tightly packed, so there is no shrinkage, but in the outer layers you have the shrinkage, which is a physical factor. The list of plasticizers of polymers containing plasticizers is very, very long and can be seen in the Handbook of Plasticizers from George Wipch. I think it's a Polish name. So, examples for affected materials, we all know them, from instantaneous or wax cylinders to shellac discs to photographic, cinematographic film materials on nitrocellulose as well as on cellulose acetate, instantaneous discs, and so on. But recently, in one of my nice little destinations, I found early polyester tapes stored under irregular climatic conditions, which showed signs of loss of plasticizer, embrittlement, and spoking effect. And this is something which concerns me, because PET usually does not have a mixture of plasticizer, but is internally plasticized, which means that the part of the plasticizer is a part of the polymer structure. It's incorporated, the flexibilizing groups are incorporated into the polymer chains by copolymerization, or so-called side chain grafting, and therefore they are linked with the material and there is nothing to evaporate. Not so with this tape. This tape shows the sign of the first signs of spoking of embrittlement, and it is BASF LGR30P, which is a well-known polyester tape, and an early one, comparatively early, 1968 to 1958 to 61, it was produced. No, 68 to 81. And it's definitely polyester. So even with such mixtures, you can have shrinkage, although you don't expect it. So facing future climatic change, all of us should be aware that this might happen, even with the most stable materials. Yeah, just let the climate become worse and worse, and let and forget about good climatization in your rooms. Yeah. What is the next huge problem? All of us know this is binder breakdown. Pigment binder instability, we all know it. Sticky shed, soft binder syndrome, oxide shedding. We all are aware that this is a huge problem, and we think classically this is a hydrolysis process and it's reversible by baking a tape. Looks like if everything was good, but so there are three theories, and honestly I believe its whole effect is a combination of everything. Three main theories. The classical theory is the classical hydrolysis reaction. A pigment binder instability is a reaction of humidity in combination with high temperature. So water, which is omnipresent in form of humidity in the air, causes a chemical reaction which is called hydrolysis. The polymers which bind magnetic particles and the backcoat in a homogeneous coating break down. The binder loses essential physical properties, and the tape starts squealing, sticking, head clogging, oxide shedding. Here is a schema of this reaction. So binders and the binders react with so in the polyester polyurethane binder, which consists of a hard and a soft segment, esters and carboxylic acids decompose to water and alcohol, and the crosslinks break, and in the worst case, for example, metal particle tapes can also corrode. But you have the leakage of the scission of the chain scission, and the result looks, as we all know, like this, or in a worst case, like this. In this case, the process of delamination, so the information on the left side here, where you can look through the tape, is lost because it's sticking on the reel. So this should never ever be the case. You should never ever spool a tape so far. So if you have a tape which looks, or which you know from the tape brand that it might be sticky, then you never ever might lose magnetic layers. So I always have a special light situation where I can control on the long low winding speed if some particles come off or not. This is the classical theory. I know. And in theory, it's reversible by tape baking, and Ampex has patented this already in 1993. You can read how to do it, it's not a big problem. But then we have another theory, and this is the theory of Mr. Charles Richardson. He tells us that this is only the case with back-coated tapes, and non-back-coated tapes are not sticky. He has a patent where he is removing the back coating from the tape and then everything is okay. But I can tell you this is not the case. And if the video was playing, I could show you that this is a non-back coated acetate tape, non-back coated, which is sticky, definitely sticky. This leads us to the third and last theory, the manufacturing process and the physics. A recent study from the Library of Congress, Andrew Davis and Fenella Franz and the colleagues have found out they wanted to artificially age samples, and they found out that they cannot, in the laboratory, provoke the chain scission. They cannot provoke binder breakdown. It's not possible. They aged it for a year under the whatever conditions, and the tape became not sticky. Why? Because the production process has such a high influence. Here you see the view of a tape manufacturing plant, and you see all these large, huge rollers. And these rollers, in the end, give the tape a certain pressure. It's the calendering roller, which presses together the substrate plus the magnetic coating. But the problem is that between the substrate and the magnetic coating, you have a primer, a thin layer of primer, which is polyester polyurethane. And now, if the calendering pressure is a little bit too high, then it presses together these layers, and migration starts from the primer towards the direction of the magnetic layer. This might not be harmful, this is just a production process and helps to bind. But if you store your tape under high humidity, under elevated temperatures, and with high pressure on a tight pack, because you are in a radio archive, and the last thing the operator did before putting the tape into the archive was high-speed rewinding and get rid of it and put on the next one. Then you have such a high pressure, then you have all the thermodynamic factors which open the pores, let water come into the material, and the pressure gets higher and higher. And then it happens that the primer migrates through the coat to the next back coating, where you also have polyester polyurethane. And then they bind together, and delamination takes place. So factors influencing this process is the relationship between thickness of the primer layer and the calendering pressure and also the production speed. They wanted to make it faster and faster and faster, and therefore this alignment was not done so correctly as it could have been done. And then you have two effects. One is stickiness, and the other is the contrary. You lose the information completely because it is not pressed hard enough together, or due to your storage situation you have these problems. So winding tension, winding speed before ending in the archive, diameter of the spool, weight and pressure of the material, storage conditions, temperature, humidity, the vapor pressure inside the material, the higher, the more material expansion. So all these thermodynamics factors lead to migration. And finally, some more challenges. One is this nice little termite residues, which you will find with the ongoing climate change more and more. Then certainly mold growing. Then maybe some insects coming into our countries from regions, or combinations of all of these factors together, yeah, loss of plasticizer, brittleness, termites, and mold. But fortunately, in our study course, we are able to restore such tapes. This is winding, and yeah, unfortunately, the videos are not linked because it's not on my stick. So thank you for your attention. This is my final slide.
Thank you, Nadja, for a fascinating presentation. I wonder if there is one question. We don't have so much time anymore.
Thank you. It can be very difficult to identify in a particular film what kind of plasticizer was used. Of course, for acetates, it's mostly TPP. For nitrates, it's often camphor, but not always. I wonder if you have any technology for identifying this, if you routinely try to identify plasticizers, and also if you collect any data on which particular film maker, manufacturer was using what types of plasticizers in which period, because that would be extremely useful.
So we have a very good knowledge about which plasticizers have been used because we have been doing lots of studies with ATR, with gas chromatography, but also non-destructive tests with solid phase microextraction, which is a technology where you have a small glass fiber inside the box and you can measure what is outgassing from, for example, from a film roll under different conditions. You can, for example, heat it a little bit up and then measure what is outgassing. The fiber is taking on all these gases and then it's heated in the gas chromatograph and then you can have an analysis. And yeah, usually the older the material, the more the longer chains you find. Phosphate, D-phenyl phosphate, 3-phenyl phosphate, DOP, and so on.
You don't use mass spectroscopy?
Okay, thank you very much.
It's
Nadja.
destructive. That's the reason.
Thank you very much.
You're welcome.
A little applause. Thank you.